Welcome to CE 402 Environmental Engineering 2 Module 4 Part 4. In this session, I am going to discuss about the trickling filters. That is the third type of filter. We already discussed the contact beds and the intermittent sand filter. The third filter is the trickling filter. This is very commonly used in the wastewater treatment plants. And this picture represents a schematic representation. This will be explained in the coming slides. And the trickling filters are used to remove the suspended solids and the dissolved organic loading from the wastewater by using microbial populations. The microbial colonies are responsible for the degradation of the organic matter as in the same case of that in the contact beds and in the case of intermittent sand filters. Then there are three processes are attached with this trickling filter. That is suspended growth process, attached growth process, and combined growth process. These three I already explained in the previous sessions. And the theory of trickling filter. The purification of aerobic decomposition of organic matter. The purification happens on the basis of aerobic decomposition. Actually, here you can see a tabular form, that is the wastewater, that is a pictorial representation, that is wastewater. It contains the organic matter, and the first filtration phase, it undergoes the aerobic decomposition, and in the second phase it undergoes the anaerobic decomposition in the filter media. And this is due to first these sand particles or the filtration materials will form a slime layer around the surface of its particles. Then it will allow the microorganisms to grow in that slime layer. And if the thickness of this slime layer is increased, then the aerobic condition will not occur. Then the anaerobic conditions persist, and it will decompose the organic matter through the anaerobic decomposition. And after some time, that is the slime layer thickness will increase, and the microorganism goes into the endogenous phase of growth and lose their ability to cling on the media surface. And then shearing action will take place, that it will shear off from the surface of the sand particles or the filter media particle, and sloughing will happen, that is the breaking up of biomass from the slime layer will happen. This is the actual theoretical part of trickling filter. This is the actual view, that is in the right side. It is the actual picture of a trickling filter, and in the left side it is a schematic representation. You can see the inlet pipe, that is the influent is fed into the bed using the rotating distribution pipe system, and this is provided for the even distribution of the wastewater on the surface of the filtration bed. You can see the filtration media shown in the brown color, and the filtration happens in the filtration media, and the filtered water is collected at the bottom of this trickling filter, and which will be collected through this effluent pipelines, which again sent into a clarifier system, and which can be recycled. That is, a portion of this sludge from this clarifier can be recycled into this influent in order to enhance or accelerate the microbial presence in the influent water. Then the components of a trickling filter, that is a rotating arm is there for even distribution of this wastewater, and a filter media. A filter media basically consists of rocks, inert plastics, aggregates or other materials, and the size of the material will be 25 mm to 75 mm, and a under drainage system is provided to in order to collect the drained water, that is the filtered water coming from the filter media. This is the actual sectional view of a trickling filter, also the plan view of the trickling filter. You can see the distribution pipelines on the top of this plan area, and the inlet influent will enter into the surface, onto the surface of the filter media through this central feeding pipe, and through this feeding pipe the wastewater enter into the distribution pipelines, and the openings provided in the distribution pipelines will helps the even distribution of wastewater on the surface of the filter media. Then the filter walls. The filter walls are made honeycombed to circulate the air. Sometimes ventilation duct is also provided. And the depth of this filters are, depth of media is 1.8 to 2.4 meter. And then the types of trickling filters, that is conventional or low rate trickling filter is there. Then the high rate trickling filter is there, that is single stage trickling filter, and two stage high rate trickling filters are there. The flow diagram is shown in the figure. First, first is the primary sedimentation tank, that is PST. The influent coming from this PST is fed into the trickling filter, and effluent from the trickling filter is fed into the secondary sedimentation tank. This is the conventional low rate trickling filter system. In the single stage high rate trickling filter, there is a slight change in the system, that is primary sedimentation tank effluent is fed into the trickling filter, and then the effluent from the trickling filter is fed into the secondary sedimentation tank, and the sludge from the secondary sedimentation tank is collected, and it is recirculated before as the influent into the primary sedimentation tank in order to enhance the microbial action in the wastewater. And this is the single stage high rate trickling filter. Then the second stage, that is two stage high rate trickling filter, there are two steps, two sets of trickling filters are used. That is, after the primary sedimentation tank, the trickling filters are used. Then after the secondary sedimentation tank, another trickling filters are used. Then from the effluent from this trickling filter will be fed into the secondary sedimentation tank again. This is the two-stage high-rate trickling filter. Then the hydraulic loading in the trickling filter. It is the ratio of discharge or flow rate to the surface area. That is flow rate divided by the surface area. The unit of the hydraulic loading rate is the meter cube per square meter per day. That is volume per surface area per day. Organic loading, it is the ratio of BOD load to volume of the filter media. That is, organic loading is quantity into BOD5 divided by the volume. Therefore, volume is equal to V is equal to BOD5 into Q divided by organic loading. Then the efficiency is equal to 100 divided by 1 plus 0.0044 root U, where U is the organic loading in kilogram per hectare per day. You can see what is a BOD load kilogram per meter cube per day, and the surface loading rate, that is the organic loading rate is the hydraulic loading rate, that is meter cube per meter square per day. Then efficiency of a high rate trickling filter, that is 100 divided by 1 plus 0.0044 divided by y root of y divided by v into f, where eta is the efficiency in percentage, not capital N. Y is the total organic loading in kilogram per day. V is the filter volume in hectare, and F is the recirculation factor. The recirculation factor can be calculated by the following equation, that is F is equal to 1 plus R by I divided by 1 plus 0.1 into R by I, the square, where R is the volume of the sewage recirculated and I is the volume of the raw sewage. Volume of the raw sewage, and R by I is the recirculation ratio. Then the operational troubles in trickling filters. There are so many operational problems related to these trickling filters, but the trickling filters are commonly used in wastewater treatment plants as the filtration system. Excessive organic loading rate without a corresponding higher recirculation rate. That is, if the organic loading rate is more, then the clogging will occur in the filter media, then ponding will happen. Then the media which is too small and the quantity of organic loading is very high, this will happen. And clogging of under drain system also will cause this ponding. Not at all the filter media clogging, the under drain clogging also will cause ponding. And a non-uniform media size or breaking up of media will also cause the ponding, and ash or debris in the filter voids will also cause ponding because it will decelerate the process of filtration through this filter media. The ponding can cause odors and decrease filter efficiency due to this ponding action. Then odor nuisance. If the aerobic action is not taken, take place in the filter media, then the odor nuisance will happen. That is due to the anaerobic decomposition. And if the anaerobic conditions usually predominate the next to the media surface, then this odor nuisance will happen. And if the slime layer growth is aerobic and decomposition is aerobic, then the odors will be minimum. If the odor are present, corrective action should be taken immediately or condition could get worse. The hydrogen sulfide gas will be produced due to this odor nuisance, that is due to the anaerobic conditions present in the filter media. And in order to minimize these conditions, these filter media to be chlorinated. Then the fly nuisance. These are tiny gnat-sized flies are called cycoda. They are occasionally found in great numbers, preferring an alternate wet and dry condition inside this filtration tank. It lay egg in the ponding area, that is the water inside the filtration tank, and it will grow to a maximum in a very short time, and it will create a nuisance throughout the operation of this trickling filter. In order to avoid this, we have to clean the sides of the filter tank using the washing system or scrapping system. Then the different parameters, that is the design values of different filtration system, that is low rate trickling filter system and high rate trickling filter system. First one is hydraulic loading, that is meter cube per meter square per day. That is 1 to 4 meter cube per meter square per day for low rate and 10 to 40 for the high rate trickling filter. Then organic loading rate, that is kilogram of BOD5 divided by meter cube per day, that is 0.11 to 0.37 for low rate filters and 0.37 to 1.85 for high rate filters, and a recirculation ratio of 0 for low rate filter and 1 to 4 for high rate filter. And the depth of the filter media is 1.5 to 3 meter for a low rate filter, and in the case of high rate filter it is 1 to 2. Then the effluent quality, in the low rate trickling filter it is fully nitrified, and in the case of high rate trickling filter, nitrified only at a low loading. Then types of high rate trickling filters, that is biofilters, then axillofilters and aerofilters. These are the high rate trickling filters used in the wastewater treatment plants. I hope you understood the theory behind this trickling filter and working of this trickling filter and the schematic representation of trickling filter, and also the operational difficulties of trickling filter. Thank you for listening. See you in the next class.